Hello everyone, my name is Denis Antipov and my talk will be about the 1 plus lambda, lambda GA on the multimodal problems, which is our joint work with Benjamin Doerr and Vitaly Karavayev. In this talk I will show that the 1 plus lambda, lambda GA can solve jump function much faster than any mutation-based EA, but it needs to use non-standard parameters for this. And we show an upper bound on the runtime for a wide range of the 4 parameters of this algorithm. Let me start with the discussion of the parameter tuning and parameter control in general. Parameter control is the online choice of the parameters during the algorithm run. And it is quite clear that ideal parameter control technique should be better than the ideal static parameters, and it is for sure not worse, because it always can choose the best static parameter. Unfortunately, there is no such thing as an ideal parameter control nowadays, and for this reason people usually use parameter tuning, because it's already quite effective and it is easy to do. There are a lot of well-developed tools and so on. However, the parameter control is a hot topic in the theoretical community because the fact that it can be better inspires a lot of researchers to dig into this topic. The research in this field is not really trivial, because to understand which parameter control techniques you need first to understand how each parameter influences the optimization speed in each stage of the optimization. For this you can do something like these heat maps, where on y-axis you have the parameter value and on x-axis you have, for example, distance to the optimum or any other state of the optimization, and the brighter the color is, the better to use this parameter at this optimization stage. And as you can see, there are different results even for one parameter, but on slightly different algorithms. And it is hard to obtain such heat maps theoretically. However, if you manage to do so, you usually can also deliver the runtime for static parameters as well. The good example of such research is the paper by Benjamin and his students, which won the Best Paper Award at GECCO 2017. There they considered the 1 plus 1a on jump function with the gap size k, and they showed that if they use the optimal mutation rate in the standard bit mutation, then they have some runtime. However, if they deviate, when you deviate from this optimal mutation rate, you have a significant increase in the runtime. And then, based on these observations, they proposed a method of dynamic parameter choices and managed to solve the jump function only a little bit slower than the 1 plus 1a with the optimal mutation rate. In this work, we want to follow the same pipeline, but we consider a more complicated algorithm. So in this talk, I only finish with the finding the upper bound on the all possible static parameters. For this reason, let us introduce the jump function more closely to you. This is a function which is based on the classic 1max function, which is a model function which returns the number of 1 bits in its argument. And jump function has a fitness value of radius k around its optimum, and it's usually used to see how the algorithm can traverse this fitness value. And this traverse of this fitness value is usually made by jumping from the local optima to the global one, and for this reason it's quite hard to do for many standard evolutionary algorithms. However, in this paper, in this work, we consider not an mutation-based algorithm, but a crossover-based algorithm, the 1 plus lambda lambda GA. But it uses crossover in a quite unusual manner, because it uses it after the mutation to repair the harmful effects of the mutation. In more details, it has a parent population of size 1, so he stores only one individual X, and then it performs iterations which are divided into two phases: the mutation phase and crossover phase. In the mutation phase, it creates lambda offspring by applying a standard bit mutation with rate lambda over n to the current individual X. However, all these standard bit mutations are made conditional on that they all must have the same number of bits which they flip. For this reason, we first choose the number L from the binomial distribution and then flip L bits in each offspring. Then the algorithm chooses the best offspring as the mutation winner, X dash, and then it performs a biased crossover between the mutation winner and the current individual for lambda times. The biased crossover takes each bit from X dash with probability 1 over lambda, and otherwise it takes a bit from the current individual X. Then it chooses the best crossover offspring, and if this best offspring is not worse than the current individual, then it replaces it. Okay, you can see that parameter lambda is mentioned here at least in 4 places, namely in the mutation rate, in the crossover bias, and in the population sizes for both phases. And there is a decent logic behind this choice of the parameters. Well, first, the mutation rate and the crossover bias are bounded so that if the mutation rate is p, in our case it's lambda over n, then the crossover bias should be 1 over np. It is made so that all crossover offsprings were in an expected distance 1 from X, because we want to make small but very likely progress in each iteration. Then the population sizes are set as Pn in order to give a constant probability to have a successful crossover phase, which means that if we have some beneficial mutation in X dash, then we create at least one offspring which has this beneficial mutation, and all other mutations are repaired. And we take the mutation phase, the size of the population for the mutation phase the same, in order to not to increase the cost of one iteration asymptotically, but on the other hand we want it as large as possible in order to maximize the probability that X dash has some unique beneficial mutation in it. However, this already doesn't work for any multimodal problem, because when we solve multimodal problems and if we are stuck in a local optimum, then we want to make a large jump to get out of it. For this reason, we consider the 1 plus lambda comma lambda j with a general parameter setting. So we use mutation rate p, crossover bias c, and population sizes lambda m and lambda c for each phase respectively. And these parameters are not bounded to each other in our analysis. And for this general parameter setting, we have the following result on the runtime. We only require the mutation rate to be at least 2k over n, and this gives us the following expected runtime for the algorithm if it starts in the local optimum of the jump function. Well, it looks a bit clumsy, but let me explain it in details. So on the example of the expected number of the fitness evaluations, here we have the cost of one iteration, so it's just the transition between the runtime in terms of fitness evaluations and iterations. And as you can guess, in the denominator we have the probability that we get into the optimum from the local optimum in one iteration. So for this we need first to choose L close to its expectation, which is constant because we use a binomial distribution for choice of L. Then there is the probability that the mutation winner x dash has all k bits flipped, all k 0 bits flipped to ones in it, so that it was possible in the crossover phase to create an optimal individual, and this is made under assumption that the number of the bits flipped was chosen close to its expectation, and then conditional on the previous two events. This is the probability that the crossover finds the optimum, which means it repairs all the harmful mutations which were made in x dash, and it keeps all the good mutations in x dash in at least one offspring. This result allows us to deliver the optimal parameters, at least they are optimal up to the e in big O of k factor. So if we take both crossover bias and mutation rate equals to square root of k over n, and if we take lambda, both population sizes equals to square root of n over k in power of k, then we have this runtime, and as you can see, this is approximately the square root of the best mutation-based algorithms runtime, which is quite impressive. And however, although we have such a good runtime, it's not too good at the moment. And actually the main problem is that to set these optimal parameters we have to know the jump size precisely in advance before we run the algorithm. And a little spoiler that we already know how to do it, and we generally followed the pipeline of the paper on the FastGA, and used a heavy-tailed parameter choices. And the second problem is that these parameters, which include also an unnaturally large population size, they are not very good for the easy stages of the optimization. For example, it's we have a too large cost for each iteration when we still have only a small progress when we are trying to get to the local optima. For sure, with small adjustments we can minimize this factor, but we cannot get rid of it. It will still be present. Well, let me finish with the take-home message. In this talk we showed that the crossover significantly helps on the multimodal problems, because it helps to escape local optimum. Although there already were some results on these fields, in this case we don't use any additional heuristics, which, for example, preserve the diversity in the population, and we don't use the parent populations at all, actually. We showed that some non-standard parameter setting is required for 1 plus lambda common j to get this good runtime. And the question is how to find this setting using different parameter control techniques and so on. And also, this setting doesn't work well on the early stages of the optimization, and so the additional requirement to the parameter control techniques which are used here is that they must also use some small population sizes when the optimization is easy. Well, that's all. Thank you.